Hello and welcome to this session. In today's session, we shall be looking at the integration by a method called Ostrogradski's method. Now, this method is useful when we are integrating rational functions that takes the form integral of p of x divided by q of x, where p of x and q of x are polynomials of some positive degree n, and the degree of p of x is less than that of q of x, so that p of x divided by q of x is a rational fraction. Now, whenever we are integrating integrals of this kind, the standard approach is often the use of partial fraction decomposition. This technique usually requires factoring the denominator, that is, we get the factors of q of x completely into linear and irreducible quadratic factors. This process, however, can be tedious in some cases, and it may be error prone, especially for high degree polynomials, and sometimes impossible in elementary terms. For example, an expression such as x power 4 plus 1 cannot be factored over the set of real numbers. Now, the insight by Ostrogradski is that you don't always need to factor q of x fully. Instead, the Ostrogradski's method offers a structured decomposition based on the algebraic relationship between the function q of x and its derivative q prime of x, which is basically the derivative with respect to x of q of x. So this method spreads the integral into two parts. The first one being the rational part, that is a fraction that integrates directly to a rational function, and the second one being a logarithmic or the inverse trigonometric part arising from simple roots, often integrates to the logarithm of x or tan inverse of x. Now, this approach avoids full factorization and provides a systematic algorithmic pathway to integration, and is especially useful when partial fractions are impractical. Now, when do you use the Ostrogradski's method? This method applies to integrals that takes the form integral of p of x divided by q of x, as we have said before, when the following conditions are met. One is that the degree of p of x should be less than the degree of q of x. So p of x should be of lower degree than q of x. Of course, if this one is not satisfied, you can first do the division, the wrong division. And number two is that when q of x has repeated or irreducible factors, when q of x has repeated or irreducible factors, and that means that the greatest common factor of q of x and its derivative q prime of x is different from 1. When the greatest common factor between q of x and its derivative is different from 1. If q of x has only simple roots and factors easily, then the ordinary method of partial fractions may be sufficient. But when that is not the case, then we may use the Ostrogradski's method. So we are going to see how to use this method to work out the problem. So the method normally is applied when we have the integral of p of x divided by q of x. And this is how we check when to use the method. We check, is theta proper, is p of x divided by q of x a proper fraction? That is the degree of p less than that of q? If that condition is not satisfied, then we use the polynomial division. If it is satisfied, then we check we differentiate q of x and then find the greatest common factor between q of x and q prime. If the greatest common factor is 1, then we use partial fractions. If it is different from 1, then that's when we use the Ostrogradski's method. So we look at this method in general. The Ostrogradski method, which is also known as the rational decomposition method, is a powerful technique for integrating rational functions that take the form p of x divided by q of x, and where p and q are both polynomials, and the degree of p of x is less than that of q of x, as we have said. This method is particularly useful when traditional partial decomposition becomes cumbersome, or when the denominator has repeated or irreducible factors. So the method can be stated as follows. So let p of x and q of x be two polynomials with real coefficients, and suppose that the degree of p of x is lower than that of q of x, so that p of x divided by q of x is a proper fraction. Then the integral of p of x divided by q of x with respect to x can be expressed as p1 of x divided by q1 of x plus the integral of p2 divided by q2 of x. p1 and p2 are polynomials, the same with q1 and q2, and p1 should be a polynomial of lower degree than q1, while p2 should be a polynomial of lower degree than q2, so that both p1 all over q1 and p2 all over q2 are proper fractions. Now, q1 is defined as the greatest common factor of between q of x and q prime of x, while q2 is defined as q divided by q1. So this integration method is what we call the Ostrogradski's method. We can look at an example where we can apply the method. We have an integral, the integral of 2x divided by 1 plus x squared. So p, because you're going to write this integral of p of x divided by q of x, then we see that p of x will be equals to 2x, while q of x is equals to 1 plus x raised to the power of 2. Notice that we can expand this and write 1 plus 2x plus x squared. The next thing we do is to differentiate to get q prime of x. The derivative of q of x will be 2 plus 2x, which we can write as 2 into 1 plus x. So that now, when finding the q of x, we ask ourselves, when we're finding the p1, or rather q1 of x, we need the greatest common factor between q of x, which is 1 plus x squared, and its derivative, which is 2 into 1 plus x. And if you look at this, the common factor is 1 plus x. This one is different from 1. So we can apply the method. Then Q2 of x can now be expressed as Q of x divided by Q1 of x. So it is this 1 plus x squared, which is Q of x, divided by 1 plus x, which is Q1 we have obtained here, to get 1 plus x. And now at this point, we apply the method. The method is given here. P of x, P1 should be a polynomial which is 1 degree less than Q1. Since Q1 is 1 plus x, which is a degree 1 polynomial, then P is a constant. Similarly, P2 should be 1 degree less than Q2. So since Q2 is 1 plus x, which is a degree 1 polynomial, then P2 is a constant. So A and B here are constants which we need to determine. So the problem is, how do we determine the constants A and B? The common approach here will be to eliminate the integrals here. How do we remove the integrals from this expression? We can remove the integrals by differentiating both sides with respect to x. So we write the derivative with respect to x of the integral of 2x divided by 1 plus x raised to the power of 2 is equals to the integral, or rather the derivative with respect to x of a divided by 1 plus x plus the integral of b divided by 1 plus x dx. Notice that differentiation normally reverses integration. So when we differentiate an integral, we shall get the integral of this function here. The same with this one. But we need to differentiate this term. This term we can differentiate by writing the derivative with respect to x of a all of 1 plus x is equals to a. Remember, a is a constant, d by dx of 1 plus x raised to power negative 1, which will give us minus a divided by 1 plus x raised to the power of 2. So when we differentiate both sides with respect to x, this is the expression we get. So now we can multiply both sides by 1 plus x squared to clear the fractions, so that this reduces the expression to 2x is equals to minus a plus b into 1 plus x, which we can write as 2x is equals to minus a plus b bx. So we have that. To find the values of a and b, we now equate the coefficients. Notice that we have the equation 2x is equals to minus a plus b plus bx. If we equate the coefficients of the corresponding powers of x, so for x power 1, we have b is equals to 2. For the constants, we have 0 is equals to minus a plus b. Notice that on the left-hand side, we don't have a constant term. So the constant is 0, meaning that a is equals to b, but b is 2. So a is also equals to 2. So once we get the values of a and b, we can now substitute back. Remember, we had the integral of 2x divided by 1 plus x squared dx is equals to a divided by 1 plus x plus b divided by 1 plus x dx, the integral. So when we substitute a is 2 and b is 2, then we get this expression. And now we integrate. Remember, the integral of 2 divided by 1 plus x with respect to x can be written as 2 times the integral of 1 over 1 plus x dx, which will give us 2 times the logarithm of 1 plus x. Then, of course, plus the constant of integration. So that our solution becomes this. This is our solution to that integral. So basically, you see now the two parts that we were talking about. The method separate the integral into two parts. That is the rational part, which is now this one, 2 divided by 1 plus x, and the logarithmic part, which is the second one, now this one that integrates to the logarithm of 1 plus x. So those are the two parts that we mentioned earlier. So basically, this is how the method works. This is how it can be applied to solve a problem. So clearly, this method works when we have an integral p of x divided by q of x, and that p of x is a function, is a polynomial of lower degree than the denominator q of x, and two, that the p of x, q of x and its derivative q prime of x have a common factor which is different from 1. So that is what you need to check before you can apply this method. Thank you for watching, and in the next video we shall talk about another exciting integration method that we call differentiation relative to the parameter. Thank you.